Yeah, so my name is Lily Zhao, and I'll go ahead and confess that my primary research interest is the radio velocity or RV detection of exoplanets. Specifically, I'm in a somewhat goofily named field, extreme precision radio velocities. And we earned this moniker of extreme by trying to achieve RV precision of 10 to 30 centimeters per second, which is roughly the speed of like a Galapagos turtle crawling, right? Like a canonically slow animal. And so that's where the whole extreme thing comes from. And it's a particularly exciting time to be in the field of EPRVs, because just in the last 3 to 5 years, though some of the spectrographs have been around for longer, we've had this real explosion of these highly stabilized, high-resolution spectrographs, which I'm showing here in both the optical and the near-infrared, which I'm showing here are organized by the precision that they reach and also the resolution of the data they produce. And so you can see that we're regularly achieving sub-meter per second precision with a lot of these instruments, and we have a range of resolutions from 70 to 150,000 plus resolution. And because we've had these instruments online for a while now, we have this huge data set of really precise, really high resolution spectra of a ton of nearby bright main sequence stars. So now that we have these instruments with the precision, this 10 to 30 centimeters per second that we're looking for, it is a particularly exciting time to be in this conference specifically, because we're now seeing that the stellar RV signals are the largest source of quote unquote error, where I really like to use the word stellar signals more, because rather than just an error of the RVs, right? What we're really seeing is that we're collecting spectra that are sensitive enough to reveal the sort of surface features that we all know exist on these complex stars. And so as the star is oscillating back and forth on the timescale of minutes to hours for the main sequence stars we're looking at, or as activity features rotate in and out, and even as granulation patterns change on the surface of these stars, we are creating this wealth of spectra that is capturing these differences to a measurable degree such that it is skewing the RV measurements that we're trying to get. And so I'm really excited to be talking about this at here because I think this is a great opportunity for this field to use these data that we've been collecting to understand more about these observations of stellar surfaces and how they're manifesting in spectra, and what is also very quickly becoming a necessity for the planet hunting side of things as we want to figure out how to model out these signals and so get cleaner Doppler shift planet detections from them. And so with this talk, I'd like to go through the kind of the state of the stellar signals and how they're being treated within the EPRV community. I'm going to start with the discussion of a project that I led for part of my thesis work, which compares a lot of the methods that are being employed in the field. I'll go on to talk about this new solar data set that we have that creates a really good test bed for testing a lot of these methods and understanding how these spectra are varying. And I'll finish with a new framework for thinking about how we treat these signals in our data that very intentionally builds the bridge between like the stellar side of things and the planet side of things. And so this method comparison project I call it the ESSP, the Express Stellar Signals Project. And the goal of this project was to use data from the Extreme Precision Spectrograph, one of these next generation highly stabilized spectrographs. It's an optical spectrograph with a resolution of about 137,000 and a demonstrated instrument stability of 3 to 7 centimeters per second. And so we gave out express data of 4 different target stars and all of the accompanying data products with it. And the idea was to allow the community to test their different methods for understanding stellar signals on the same data set. And so we could create this kind of like apples to apples comparison of how stellar signals were being treated throughout the field. And so we ended up getting a really nice buy-in from the community. We had over 50 participants that tested 21 different methods on the same data set. And one of the things that we immediately noticed is that these different methods operate on many different data levels. And so if we consider the sort of different data that the EPRV field is using, so I'll order them here from left to right across the screen by increasing data, and talk about the 4 major categories of data products that the EPRV field is using. Historically, indicators were the way to go. And so you would take your observed spectra and you would boil it down to a single measurement of how much activity you think was present in the spectra at the time. And so the S index, things like H alpha emission are canonical examples of this. And so you would measure, say, the core emission of a line, you would plot it against RVs, you would fit a line, you would subtract out the line, and you would call that your RV correction. Since then, there's been some other work where instead of fitting a line, they might fit like a Gaussian process, which is a much more flexible model or allow for some phase lags in the data. But still from this process, from every single observation, you get exactly one value, one activity, or on the order of one activity indicator for your entire spectrum. Many other methods will make use of the CCF or the cross-correlation function, which takes your spectra. I've shown an example spectra here with just 3 spectral lines as an example. And you scan this binary mask shown in orange. And so you'll scan this binary mask across your different spectral lines. And so the primary use case was when the binary mask lined up with the value of the different lines. That's the RV shift that you would calculate. But as you shift it, you also sample the line shapes of all the lines in your spectra. And so you get this nice profile that represents the average spectral line shape in your spectra, but it does combine all of the data and average it out, and so into just one profile. And so depending on the resolution that you scan it at, the CCF gives you about 200 points per observation as you sample those average line shape at each of these mask shifts. More recently, people have kind of like riffed on the CCF method and gone to the line by line, where now each line is treated separately. And so very similar to the CCF profile, we look at each line individually and get a unique profile from that. And from this, we've seen that different lines will react differently to activity. Some will be more sensitive to activity, some will be less sensitive to activity, and some will even be negatively correlated with the effects of activity. And so from 200 points per observation, we now have maybe 10,000 lines per observation that we're looking at and that are showing unique features that reflect the impact of stellar signals on the spectra that we're gathering. And even more recently, there's been a push, since we now know that spectral lines will react differently to the stellar surface variations that we're seeing. There's been a push to using the full spectrum, where I've no longer made up the spectrum. This is an observed spectrum. And on the points, I'm showing the residuals from a template spectrum, either red or blue. And I've masked out very generous margins for any telluric lines that you might be seeing, and also any that fall within the error of uncertainty. And you can see that for different observations, all of these different pixels are changing at different times and in different ways. And so if we overplot them on each other, we see that for all of the pixels in your spectrum, they really change in statistically significant ways and carry information on how the stellar surface is varying in the observations that we're collecting. And if we use the full spectrum, you get the 500,000 pixels per observation, and you preserve the most amount of information about the star that you're observing. And so back to the ESSP, we saw that there was these range of methods, which I've grouped here by like the input data that they use. And they also operated around 3 main philosophies. So the main philosophy was the first one is this idea of like a activity metric. So very similar to the activity indicator idea, but like novel ways of discovering indicators rather than finding the core emission. A very popular approach was using principal component analysis, or PCA, to find like the largest axes of variation and use that to construct a time series of the amplitude of these variations across your observations. Beyond metrics, there was also novel ways of approaching how to exactly use this information. So like the mitigation method, before it was fitting that straight line, but now, as I mentioned, there was a lot of Gaussian process-based methods, or moving to the Fourier space in case there was a phase lag between the indicators that you're measuring and the RVs that we're seeing. And lastly, there is this idea of separating out the different aspects of like a orbiting planet versus the stellar surface variation based on what we know about the respective variations. So for example, we'd expect stellar surface variations to give rise to asymmetric features. And so perhaps you could construct a method that would only be sensitive to translational shifts and use that to kind of get a more cleaner version of a Doppler shift and things like that. And so we had all of these methods tested on the same 4 data sets. And so here I'm showing the time series of RVs for the different data sets that we distributed to the community. They range kind of in activity level. You can see how there's like more scatter in some of them. Some of them had more observations, or the time sampling changed between the observations. And what we found is that the results of the methods varied widely by data set. So now below each time series, I'm showing a bar graph where the height of the bar corresponds to the scatter in the RVs with the activity signal removed. And like, I get it, you can't read the bottom line. Please don't try, I totally understand. But the bar graphs are ordered by decreasing RMS. And so the methods will appear at different locations along each of the time series, but they'll be the same color. The color corresponds to the data input. Sorry, I'm using the mouse and no one can see it. They correspond to the input data. And you'll notice that even just looking at the colors, they vary from data set to data set. And so depending on which star we were looking at, a method would perform differently. Doesn't even seem to be any coherence with like the approach. And so if you global observations. You'll note that along each plot, there's this dashed line that shows the original scatter in the RVs. So all the methods are doing something. They're reducing the scatter in a lot of various ways. But still, none of them are reaching this like 1 meter per second scatter that we really want to earn that extreme precision that we claim that we do, right? And none of them are reaching the like about 0.3 or the 30 centimeter per second error that is the base error expected for these observations. And maybe that's to be expected because this is real data sets, so they probably do have planets around them. So there's probably some residual planet signals here. There's instrument systematics that we haven't resolved. And all of these different methods with these different approaches have different sensitivities to these different variations. And so because we don't have like the quote unquote answer at the back of the book, it was really difficult to tell what these methods were truly modeling out and what they were removing. But if we focus in here on one of the data sets, we notice that some of the methods are returning similar scatters in the end, right? And they're all working on the same data set. And so you might think that because they're working on the same observations, if they're returning similar results, they're probably modeling out the similar signal that's present in all of the observations they're working with. And so to test this, we paired up each of the methods. And so here now we have this like almost correlation matrix. And the marker at each of the vertices is colored by their Pearson correlation coefficient to see how correlated they are with each other. And the square markers are ones that are significantly correlated. And so you can see here, I've highlighted in green also, again, the methods that are returning the similar RVRMS. And even for those that are returning similar results, they're not necessarily tracing the same signals. And so we found that we have all of these mitigation methods, and they're all good methods. They're all doing well, but they vary so much in approach and the things that they're modeling out that the results are also really varying. And so it was very difficult to kind of assess No. And so with the sun, we can remove all of the planet signals of interest, planet 9 not including. And with the 4 different instruments, we can also get a grasp of the different instrument systematics that are in our data set. And so we can create this data set that just has true, real astrophysical signals in it of the star, so that's the sun, which is also conveniently very well characterized by many of the folks in this room. And we have a grasp of all the instrument systematics as well, because we have this buy-in from the larger community. Oops. Let's see if I can. And so this is the data set that we combined. We looked at a month of data from HARPS North, Express, and NUID. And you can see that the data set does in fact agree pretty well with each other and capture real effects of stellar signals. And so I've also shown the SDO images of some of the peaks and troughs in this data set. And if we zoom in on just a few of the days, picked purely because they had the most observation from these telescopes, no other cherry picking done, we can see how even on sub-day timescales and even on hour-long timescales, they're tracing the exact same signal, which was so satisfying to look at. I did not want to be the one breaking the news to people that their instruments weren't working. But luckily, they are. And if you look at all the residuals across the comparison of this data set, you find that if you take into account the different errors that are expected with the instrument, there are only 15 to 30 centimeters per second of scatter that is unexplained. Furthermore, these comparisons are only going to get more interesting because these solar telescopes are continuing to collect data. And so as we approach solar maximum, we'll get more and more sampling of the different activity states. Right now, we've compared a month of data, and there's also work being done to combine for Express and NUID a much larger swath of data to better understand what these solar telescopes are capturing. And many more solar telescopes are coming online, and you can see that we'll get much more. So in the solid lines, in the red to blue colors are the observations that we're currently capturing. And we can see that with the addition of the other instruments, we're not only getting more time coverage across the day, we're also getting a lot more telescopes in the same location. And so you have a much larger amount of overlapping data that helps us make these comparisons. And so these sun as a star observations are a really promising way to understand how stellar signals are manifesting in these extremely high precision spectra. And we see that the data is also agreeing very well. And so we've constructed this incredibly powerful data set that captures real stellar signals in EPRV data at extremely high SNR and high cadence, and for which the instrument systematics are very well understood. And so it's a really exciting time to be in this scenario, considering these stellar changes, because we have so much data that of like a different caliber that may reveal a lot of the features on these stars. And so one of the things that I've been thinking about is how to best harness all of the information that you get in a spectra, because you have all the information in each of the pixels, but that also introduces a lot of data problems and a lot of issues with constraining your methods in the best way to get a mitigation method. And so one of the frameworks that I'm thinking about is how to boil down the question of variability in a spectra in a computationally useful way. And the framework that me and a few of my collaborators at the Flatiron Institute came up with is starting with this like multi-component picture of the sun. So here we're looking at the solar surface again. And imagine that it's broken up into these like different patches, right? And so each of these patches will have different parameters associated with them. They'll have an RV shift, whether it's oscillating towards or away from you, and it will vary across on the edges. And of course, the star will be rotating towards and away from you. And so each of the patch can be assigned this sort of like Doppler velocity field. You'll have different spectral components from each of the different patches, whether it's like slightly lower effective temperature from a spot, brighter, or different spectral components from different granulation realizations, things like that. And we know from data-driven methods like Melissa Ness's Cannon that this is in fact the whole set of spectral variations due to different stellar parameters also has a low dimensional representation. And lastly, the different components will, of course, have different intensities associated with them. Spots will be darker, faculae will be brighter, limb darkening comes into effect, which would also affect the spectral components. But that's just a one-dimensional measurement. And so if each of the relevant parameters are low dimensional, then the thing that you can conclude is that the set of all possible variations in spectra due to stellar surface variations is also compact. Or in other words, there's a low dimensional representation that will faithfully reproduce all the variations that you expect to see from the spectra you collect of these varying stars. If you don't believe me, I'll try and prove it to you. So we test this framework using an extremely simple spotted star model. So we put some spots on a surface, we paste it onto a star, and using Starry, we simulate spectra where we've assigned one spectral component to the quiet star. Here's just a cartoon representation. I promise there are more lines in our real data. We give the spot another spectrum, and using the properties of Starry, we also consider how the spot will rotate relative to the quiet stellar surface. And so using this, we can use Starry to construct a spectra, which we'll denote here by x sub n. And we can also construct two relevant basis vectors in this space to kind of capture the stellar variations we expect to see. And in this very simple model, all we had to do was take the difference between the quiet and spot model to see the difference between the two spectra, and also the difference between the quiet model and the rotating spot spectra. And what this does is give you two different basis vectors that are respectively sensitive to the visible spot fraction, so the presence of the spot spectra on your star, and also the spot Doppler distortion, so what changes as the spot rotates in and out of view. And so here I'm showing a time series of a single spot rotating in and out of view, and you can see how it leads to these spurious RV measurements where I've injected no RVs, so all of these RVs are due to the spot measurements. And here I'm showing in projection space the curve that's traced when you project these spectra into this spot fraction and Doppler distortion space. And you can see that it forms this coherent surface in this carefully chosen projection space, relating to the fact that the spot is rotating on a coherent stellar surface. And so it's something, because we constructed the projection space carefully, that we more or less expected. Furthermore, if we do this for a grid where the spot sizes get bigger or the latitude changes, you can see that this loop that it creates in the projection space scales with these spot properties. And so by carefully constructing this latent space, we've constructed this area in which we can take these projection values and map them to the spot properties in the observed spectra that we're seeing. And so we now have a hint of what the surface of a star looks like just from looking at the spectral changes present in the integrated spectra. And indeed, if we look at this grid of spot sizes and we look at the measured RVs, you can see as the spot gets bigger, the RV amplitude gets larger as well. And here, because it's like a grid, I've added these like green shaded regions to indicate the 10 centimeters per second, the target of the EPRV work. And so if we overplot the corrected RVs, you can see that it successfully removes all of the spurious RV measurements from the spotted star alone. And if you look at the residuals, they're on the order of the 10 to 30 centimeters per second that we're looking for. And this is in the case where it was just the sun that we're looking at. And if we add a planet, and so here the planet has an amplitude of 0.7 meters per second, we see that in fact, the planet signal is preserved, and we get very similar residual scatter to the case where there was no planet. And so by carefully constructing this projection space, we've created a representation that both informs what your star surface looks like from the spectral changes alone, and is agnostic to planet shifts and removes only those properties, which is helpful for preserving planet shifts in the EPRV data that we're looking for. And so if I had to say there was one big takeaway from this talk, I would beg you to remember that the EPRV field is producing this very high precision, very stabilized spectra that I think would be very helpful for a lot of the efforts in this room for understanding what's happening on these different stars. And I think it's a really exciting opportunity for stellar scientists and very much so a necessity for the planet hunters at this point. And so I'll stop there and I'm happy to take any questions. Thank you for your time.
All right, let's take some questions right here. No. Now I don't have a mic.
You can speak loudly though.
Yeah,
I trust you.
I'm Tom Bernard, Space Science Institute. Thank you for a great talk, great topic. Have you looked at what kind of compact surface P-modes make? Because there is a specific signal of P-modes that the velocity amplitude grows with height because of the density gradient, so that your spectral lines are actually waving like this. They're not going back and forth like you would from a planet.
Yeah, so the question was whether we had considered what sort of basis would represent P-mode oscillations. And it's a great question because here I've shown a very simplistic example that really only considers spotted stars. But you're completely right. The same logic applies to other sorts of variation as well. And so the P-mode oscillation would be introduced in the RV shift of the different components, and it would lead to the spectral changes that you outlined. And so this is like kind of like a first step in the direction of getting a fully fledged method that would work for a variety of stars and that would work for real data. And the careful construction of a basis vector to get those sort of variations that you talked about, things from granulation, that's where like the real like work comes in for making this something that can be applicable in a very large scale kind of way.
Right here, Derek.
So it occurs to me that, real spots are more complicated. On real regions, there's diversification, there's spot evolution, all of those things. Now, I mean, clearly that's going to make your representation less compact. How easily those kinds of physical effects fit into your model?
Yeah, so the question was, as we incorporate more like complicated spot features or activity features, how does that affect the compactness of the space? And so I would argue that while spots certainly are more complex, they lie along the same axes that we're already considering. So their spectral parameters might change, but it would still be on a very low number of axes. And incorporating more of them will definitely lead to a more complicated, definitely higher dimensional than 2 projection space. But it's something that doesn't break the fundamental assumption that there's like a finite low integer number of dimensions.
All right, next question. Right here. Oh. People are like waving me over to a question and I don't see the question. All right, we got one in the back here. If you're in back, you have to make a big wave. There we go.
Thank you. This is
Name
Manuel
it.
from
Name it.
Madison. Thank you for a great talk. Kind of a related question to the last one. So in the example you show, of course, we are looking at this artificial or star in kind of in a sun, like we observe the sun, right? So we have this privileged geometry. Are you worried about some of the degeneracies that might occur when you are in a completely generalized situation, like you are looking at the poles of the star, with all these different geometries and possibilities. Are you worried about any of the degeneracies that might occur because of this? Thank you.
Thank you for your question. So the question was about whether I'd be worried about any degeneracies when we consider all of the possible orientations of real stars. And that's a really good question. And I think it kind of goes back to the point that this is a framework that's true, but to implement it, to like craft a projection space that would be sensitive to those things and not sensitive to planet shifts is kind of like the crux of the question now. And so this work is more showing that this is a way that you can approach the problem. The math works out, the derivations is true. And a simple model, all of the things that we expect to see do happen. But as we move to real data, as we move to more complicated stars at a variety of orientations, it's very likely that the specific method of the projection space or the parameters that you have to take into account are going to vary from case to case. And so it'll vary with like what your star is doing, what it looks like, how it's facing. It'll vary with what data you've collected, what the SNRs, with the wavelength ranges, et cetera, and stuff like that. And so it's a very good point. It's definitely something else we should consider. And it's just something that will have to be left to future work.
Right, we'll wrap it up here. Thank you very much.
Testing, testing, testing.
Okay, you're good. Cool. All right, our next speaker is going to